Cool. So let me start again. So hey, so I work at Datadog. So if you don't know what it is, it's an observability platform that lets you have a look at your stack, at your technical stack, from the front end to like all the way up to your architecture, and like figure out what's going on and fix errors if there are any. So I'm also, in my spare time, I'm the maintainer of this TypeScript library called TS pattern, which is an implementation of pattern matching for TypeScript. So if you are not familiar with the concept of pattern matching, it's essentially a switch statement. It's essentially a way to have code branching in your TypeScript code and to be able to branch on the structure of a value instead of a single value. So for instance, here, I'm branching on this result value. As you can see, it's a union type, and it also contains a union type in this property. And so it lets me like match on the pattern of my value on the using this value here. So what I'm essentially saying is that if I have a type OK and the data that has type text, then execute this branch of code. And so I'm showing you this because while I was working on this library, I had to learn a lot of stuff about the type system, and yeah. So just before I begin, quick show of hands: how many of you use TypeScript at work? Okay, pretty much everyone. Okay, so I hope you are not you're like it's you're going to get something out of this presentation. So what I want to do here in my library is to narrow the input type of my result thing down using the pattern I got on the right. So here in this helper function, I want my result to be like of type subset, of type OK, sorry, and of type image, right? And so it's actually pretty complicated. And another feature of the library is to check that you are handling all of the possible cases. And it's another thing that's pretty hard to do. And in order to do that, you need to have some like real kind of programs, but at the type level. So here's my presentation. So I want to tell you about programming with types. And yeah, so it's going to look a bit weird to some of you probably. Yeah, so I want you to be in the play mindset. I don't want you to like try to find an application for what I'm going to tell you, because it's going to look weird, but it has application. It's actually quite interesting. Okay, so yeah, wait, can I hide this? No, sorry about that. Okay, so the TypeScript type system is actually Turing complete. So there is this guy who opened an issue on the TypeScript repo, I think a couple of years ago, or yeah, it was in 2017. And he made a formal proof that the type system is Turing complete. So it means that you can write type signatures that actually can evaluate to any program, any possible program, and solve any possible problem. So that's kind of a big deal. And yeah, and so it gives us a lot of power, and we can do a lot of stuff only with types. So I want to show you, I want to essentially show you the building blocks that you are familiar with on regular programming languages, and show you that you can use kind of the same problem-solving mindset at the type level that you would be using with regular values. So I'm going to go through conditional branching, variable assignment, functions, loops, and all of that using type signature only. And it's kind of annoying. And yeah, and so there is like a huge type signature on the right, and I would like this kind of code to feel a little bit less scary at the end of the talk. And yeah, like I want it to feel like something you can understand. Okay, so why should you care? So here is here's the Venn diagram, and it's showing the set of all programs that are well typed, so it passes the type checking, and all programs that are correct, so it does what you want them to do. As you can see, there is an overlap, but it's not it's not complete, like it's not overlapping completely. And it means that you can have some programs that are well typed, but don't do what you are actually expecting. And you can also have programs that are correct, but are not well typed. And since most of us have been coming to TypeScript by migrating existing JavaScript library, it's actually something we usually have to do, like type some code that is pre-existing, and that sometimes can be pretty hard to type. And one example is this function called curry, which exists on Ramda and Lodash and other utility function libraries. Curry, what curry does is that it takes a function and returns a function. The main difference is that if you don't give all parameters to this function, it will actually return another function taking the rest of the parameters instead of returning an invalid result. And as you might imagine, it's pretty complicated to type that in TypeScript, even more so because you have this whole special value that you can pass to your function, which should be taken into account in order to provide a function that takes this parameter on top of the other one. So so there is a great article by Pierre-Antoine Mills explaining how to type curry specifically, and that's how I learned most of that stuff. And so on our diagram, curry would be here. It's a correct program, but it's pretty hard to type. And what I'm going to show you is a way to push the set of well-typed program further on top of the set of correct program, and in order to cover the curry case, for instance. So it's really something that you can apply. Yeah, at Datadog, we obviously deal with a lot of data, and most of this data has a tabular shape. So it's essentially tables. And tables have columns, and each column can contain different type of values. And some of the use case we had was to build this data frame class, which is a data structure. It's parameterized by a list of columns, and each column has a different type. And you want the get column value method to return the right type for this column name, right? So if I get the column values for name, I want it to be a list of string. I don't want it to be a list of string or number because it's not super useful. So that's something I show you how to do. Great. So how to program with types. So the first thing I need to tell you is that so TLTS, that's how I call the type system of TypeScript. It means type level TypeScript. I'm the only one using this, but I'm going to use it throughout of this slides and the presentation. So TLTS is a minimal purely functional language, meaning that just like a purely functional language like Haskell or Camel, and Camel is not pure anyway, like some other languages, it only has functions. And so you can do conditional branching, you can do variable assignments, functions, loops, equality check, and like a lot of other stuff. But some of the things you can't do is mutable state. You cannot have a variable that you update over time. It cannot do input output, and that's fortunate. We don't want my type system to read my files. And it doesn't have higher order functions, which means function taking other functions. So another way to say that is that functions are not first-class values in TypeScript, in the type level of TypeScript. So the first thing I need to tell you about is the data we will process. So like any programming language, type level programs transform some data, but unlike most of them, they transform types. So the data we are going to deal with are types. So what's our disposal? So we have the primitive types, number, string, Boolean, that kind of stuff. We have literals in TypeScript, like the type 20, which has only a single member, which is the number 20. And we also have data structures like object types, tuples. So tuples are essentially lists with a fixed number of elements, and each element can have a different type. And we have lists, and lists are contain a variable number of elements, but they all have the same type. Another thing that I think counts as part of the data structures are union intersections. And yeah, so we usually think about them as operators, sorry. But I think they are more like constructors because we can actually loop on a union type. And I'm going to show you how to do that. So that means that you still have access to the members of, so it's kind of more like a list or a set than an operator. It doesn't evaluate to a single type. Okay, and types in TypeScript are sets. So for instance, the type string is the set of all possible strings, and the type hello or bonjour is the set that has two members, the hello string and the bonjour string. So pretty basic. So some sets are infinite, like string, and some of them are finite. And they can contain each other, right? You can have sets that contain other sets. And everything is contained in this unknown thing. So the union constructor returns the union of two different sets, right? And intersection, the intersection of it. And so, yeah, so the unknown type is a superset of every other type. So it's kind of the outer circle in this picture. And so when you do A or unknown, it's actually the same as unknown, and A and unknown is actually the same as A. There is also never. So never is the empty set. We can think of it like this. So it's kind of, it's like an empty list, kind of, because when you concatenate the set hello and bonjour with never, it evaluates to hello and bonjour. It's the same thing. It's like an empty list. And we also have any, so I'm not going to tell you a lot about it. It's a bit weird. It's a bit everywhere like this, because it's the superset and the subset of every type. So, so that's why TypeScript is not considered like a sound type system in the like programming language community. And that's on purpose. That's to make the migration of from JavaScript code base to TypeScript code base a bit easier, but it makes this special type a bit weird. So yeah, to sum up, the data we are going to deal with are types. We have primitive, literal, and data structure types. All types are set in TypeScript, including types with a single element. They are a set with a single element. Union types are data structures. Unknown is the superset of all the types. Never is the subset of all the types. And any, we won't talk about it. Okay, so let's move on to functions. So in TypeScript, functions are called generics. So they're defined like this. So you have this type keyword and the name of your function, and then some parameter and some code. This is called the type parameters. This is called the return type. All of this is a generic, pretty basic. So this is a function returning the union of two types. Not super useful. Here is a little bit more useful example. A push function that takes an element and a list and appends the element to the list. So here something interesting is this x's extends any array. And this is what we call a constraint. So it essentially says that whatever you pass as second argument should be some kind of array. So more precisely, it should be assignable to any array. Great. So now code branching. Moving on. So code branching is done with conditional types in TypeScript. So this is this kind of ternary operator we have. And so what you are doing is that you use this extends keyword again, but it doesn't mean the same thing. It means that it's kind of a question. It's is A assignable to some other type? So in this case, is A assignable to true? So the only way this can be true is that if A is true. So so you can think of it as an equal here. And in this case, we return this, otherwise we return that. So if you do if true number Boolean, you get number. Simple. Yeah, so A extend B means that it's assignable to B. And assignability is like a whole interesting topic, and I won't cover it fully, but yeah, but so something I can say that it kind of looks like pattern matching, what I told you about at the beginning of the talk. So you can check that the data structure matches some like some shape you would like it to match. So to be more concrete, you can implement this XOR logical door with two booleans like this. So you wrap them in a tuple and you make sure that it extends a tuple with true and true, which is essentially the same thing as making sure that n is true and m is true as well. So that's a pretty convenient way of doing this. And you can have like deeper nested structures and you can compare them like this. So if you want to write a type level function that checks if the user is Gabriel, which is not super useful, but you get the point. You can do it like that. Like, is it an object with a name property, which has the type Gabriel? The noise is coming back. Okay. And the team property, which is an object with a name Database, then it's me, otherwise it's not. And so as you can see, if you give the wrong name, it doesn't work. If you give the wrong team, it doesn't work. So that's pretty handy. And you can also extract stuff from this data structure. And that also makes it even more like pattern matching. So in this case, you can use this infer keyword. You can only use it in the right-hand side of the extend keyword. And it lets you declare a variable and extract it from a type that can be a parameter. So in this case, I'm extracting the team type from the user, right? And I'm returning it. No questions about that? Cool. By the way, if you have questions or anything, you can stop me anytime because I'm going to show a lot of code. And if that's not clear, feel free to say so. So variable assignment. So one trick you can use using extends and infer is to use infer right after extends. And that's actually a way to assign some computation at the type level to a variable. So if you have this function doing some heavy computation and you want to reuse the result several times, like in this case, I'm putting it 3 times in a tuple, you can do it like so. So it's a way to make some like performance optimization on your types. Okay, loops. So now it's getting a bit more challenging and a bit more fun. Like I think. So there are 3 different ways of looping on types. You can loop on object types, on every keys of an object. You can loop on tuples. We will use recursion to do that. And you can use on union types. So I'm going to show you how to do it. So let's start with objects. So we have mapped types in TypeScript, and they look like this. So these are generic functions, generics. They take some object, and you can loop through the keys of this object by using the in keyword followed by the key of keyword, right? And that's a neat way of updating all the keys of an object. And something interesting is that it preserves the relationship between the key and the value, right? So here, if I do t of k, sorry, I get a number, the first iteration, and then string, and that helps me like keep this relationship. Cool. So now let's talk about recursive conditional types. So that's the way of iterating over tuples. So you might notice that tuples are pretty similar to arrays at the value level because you can iterate on them because they can have several elements of like several types inside of it. And so you might not use them very much in your day-to-day code, but actually when you do some like these kinds of type level computation, usually at some point you will have a tuple. You usually transform your objects into tuples and then you iterate on them and then you construct an object from them. So it's like if you want to remember something from this talk, it's really this couple of slides I'm going to show you. So we can write this includes function that's similar to arrays.includes. So it takes an element, a list, and it outputs a Boolean saying whether or not the element is inside the list. And it looks like this. So you can use extends infer head, infer tail. And that essentially splits the list in 2 parts, the first element and the rest. And so here we say that if head extends x, then we return true. That means that x is indeed inside the list. Otherwise, we recurse on this function. We call it on the other branch. And if our x's thing does not extend that, it means that it's an empty list. So it's false. Empty lists don't contain anything. Any question about that? So the question was where does the tail come from? So it's extracted from the x's thing here. Sorry. So when you do infer, it's pretty similar to doing like var or let, right? Except it's like destructuring essentially. So it's destructuring, but at the type level. Cool. So yeah, so this was a reduction operation. So if you are familiar with reduce on arrays, this is this is essentially doing a reduction. It's transforming a list into a single value. So now let's show a filter operation. So as you can see, the basic structure is exactly the same. You have this x's extend, sorry, it's not capitalized, extends, infer head, infer tail. By the way, I sometimes name types with lowercase instead of like a, yeah, it's like I'm not really respecting the TypeScript convention because I feel like it's adding a lot of noise, especially when you are only dealing with types. So even if it's lowercase, it's still a type. It's just a type variable. So the structure is the same. We recurse on the list and we do something with it. But in this case, what we are going to do is that if add extends number, so if add is a number, we'll keep it in the list. Otherwise, we will drop it from the list. So here, I don't know if you see, yeah, is it big enough? It's readable. So here I have a tuple containing both strings and numbers. And here is how to filter out strings from the thing. Cool. Okay, so now let's let's implement a map operation. So as you can see, it's almost the same thing, except I'm not filtering any element from the list. I'm actually transforming every element into something else. So here I'm saying if add extends to, sorry, then true, otherwise false. So this is kind of my mapping function or my mapper function here, right here, and then I'm recursing. And so I'm transforming my list of numbers into a list of Booleans. And yeah, so you might be wondering, why can't we have a map type that takes some function and that abstract over this looping logic, and then give like a function to this function, and where I have a is2 function, then I can reuse, sorry, there is a typo, it should be just map here. And then I can give it to map and have a general way of looping through my tuples. Well, we cannot do that because it's not possible to pass a generic type to another type. It's not actually a type in TypeScript. It's something that will evaluate to a type at some point, but you cannot. It's not first class. You cannot pass it to a function. So that's kind of sad. It would be nice. Yeah, and so the last thing I wanted to show you is how to loop over union types. And this one is really weird, I've got to admit. So the way you do that is by doing my union type, which is name in this case, extends any. So as you probably know, this will always be true because everything extends any. But the name like a variable here is going to to be inside of this block each element individually, right? So if I do T is name is an object with a name property, which is this name type, I get this, right? I get an object and this name is a union type. But if I do it like that, I get a union type. And it's like I mapped this block of code over every element in the union. Right? It's a bit weird, right? But yeah, so let me show you. So I don't know, do I have how much time do I have left? Does it feel long? I can go ahead. So yeah, it would be hard to code with a mic in the end, but no, actually, I won't do it because unless somebody wants to, like is okay to hold me the mic, but I'm sorry about that. Cool. Thanks. Okay, so this is very small. This is even smaller. Okay, so we are back to the problem we had in my previous slide, where we have this columns tuple, and we want to extract the values of one of the column, right? So we want to give this function the columns plus an ID and get back like what the type of the values properties of this column. So here I should T should evaluate to a list of strings. Age should evaluate T2, sorry, should evaluate to a list of numbers. And since this doesn't exist, this should be never. So let's do that. So we are going to use conditional recursive type. And the structure is the same. So columns extends infer head. So extracting the head of the list, infer tail, question mark. Otherwise, I'm just going to return never. And so here, yeah, so what I want to do is to check if my head, like the head of the list, has the right ID. And if that's the case, I want to return the type of values. So I'm going to kind of pattern match on the head. So head extends, oops, sorry, ID colon ID. So if that's true, that means that the ID is, this is the right column essentially. And since I want to return the values property, I can extract it using infer and return V here. Otherwise, it means that it's not the right column, so I need to recursively call my function with the ID. Let me indent that to make it a little bit clearer. And so let's check if it works. So here I get a list of strings, I get a list of numbers, and here I get never, as expected. So as you can see, it's a regular recursion, nothing extraordinary going on here, except that the syntax is a bit weird because those are types, but otherwise it's like you should be familiar with that kind of stuff. Yep, thanks. So obviously, this doesn't come for free. It has some trade-offs. And here they are. So the first thing is that doing a lot of type level computation like that can sometimes slow down the compilation time of your project, which can be a big deal. It can impact the work of like all of your coworkers, so you should take that seriously. It's like, unless you are doing very, very expensive stuff with your types, which is usually not the case, you should be fine. But it's definitely something to keep in mind. So it's super hard to debug. There is no console log, obviously. So the only way you have to debug is to assign the result to a type and over the thing and check what it evaluates to. Sometimes it can be hard to track where the error comes from. And if you type a function with that kind of generic type, the error messages can be pretty bad. It can be improved, but yeah, probably like you need to account for that and to make sure that it's not completely opaque to the rest of your team. But in some contexts, it's definitely worth it. So if you are maintaining a library and you are willing to invest the time of writing like types that really captures the invariance of your library, it's something you can use and it's fine. Okay, so in conclusion, yeah, so the type system is a real language, so anything is possible. You can, so once you know like those building blocks I just talked about, you can apply the same problem solving techniques and mindset you have with regular code to types, which is interesting. And this comes with trade-offs, so don't use it too lightly if you are super good with that kind of stuff. If you want to get better at this, there is this GitHub repository called Type Challenges. You might already know it. It's pretty famous. And there are a lot of exercises, and you can get better very quickly. It's pretty nice. Thank you. Any questions? No? Are you still alive? Yep. Yeah, so I didn't hear very well, but I think the question was about the limits, the recursion limit of TypeScript, which is of 50 recursions, right? So if you already did that kind of stuff, you might hit the like hit the limit, the hard limit of 50 levels of recursion in TypeScript. So the call stack cannot go, cannot be more than 50 function calls, which is annoying. Yeah, so actually 50 is a pretty good number. I think it's enough to do some interesting stuff. You rarely have more than 50 elements in a tuple, for instance, but that can happen. In this case, the easiest way to deal with that is to convert your tuple into a union type, and then you don't have a limit. So you can loop on your union type, and then you convert it back to a tuple. So that's a way to go around it. The good news is that I don't remember his name, the main maintainer of TypeScript, like the guy at Microsoft. Yeah, whatever. He recently merged the PR to increase this limit to 100, and to implement tail recursion optimization. Which means that if your function is what we call tail recursive, which means that it calls itself without having any, like keeping any context in this function scope, it just calls itself with everything as parameters. The limit is of 1000 because it can be optimized because you can get rid of the call stack entirely, since it doesn't hold any information. You're welcome. Okay, thanks again.
So we did 3 talks on 6, and we already spent 1.5 hours. So I propose that either we do an extra talk or we take a break. Maybe we can take a break.